had a discussion on how much heat is required to cause a certain amount of temperature. And we said that whenever two objects are put together, they're in thermal contact and they have a difference in temperature. What's going to happen is there's going to be a heat transfer from the object with a higher temperature to the object with a lower temperature. This kind of heat transfer is actually quite important. Almost every day, many processes in the universe are undergoing such a heat transfer. However, in all those processes, the universe only employs three ways of transferring heat. The first one is conduction, probably the most familiar to us. And the second one is convection, also quite familiar to us. And the third one is radiation. This is the kind that we will primarily focus on, at least in the context of radiography. Now, a brief discussion, kind of like a simplistic definition of what conduction is. It's basically the transfer of energy via the collision of molecules. Here, the collision of molecules is not at it's at a microscopic level. So the motion, the particles or molecules that are colliding, this kind of collision is occurring at a small scale or molecule level. It's not macroscopic but microscopic. And in order to allow such a collision of molecules, that is, molecules of a hotter object with the molecules of a cooler object, what's necessary is that these two objects have to be in physical contact. So in order for us to employ, or in order for us to observe heat transfer by means of conduction, here physical contact is necessary. So in order for two objects to be in thermal contact and transfer heat by conduction, they have to be physically touching. You might be familiar with this method. For instance, you have a cup of coffee. Inside the cup there's coffee which is warm, and typically the cup, when they serve you the coffee, is initially not as warm. You put your fingers around you put your hand on the cup, and after a long time, you might need to switch hands because eventually the heat from the coffee is in contact with the coffee is in contact with the cup, but the cup is also in contact with you in physical contact. So there will be a transfer of heat or of energy from the coffee, which is hot, through the cup to your hand, which is the object with a lower temperature. And in all of this, the motion, the collision of particles is not macroscopic but microscopic. It's the molecules of the coffee colliding with the molecules of the cup and transferring energy, and eventually the molecules of the cup also acquire energy, hence their temperature increases, and they eventually collide with the particles that form your skin. The skin on your palm. And by this kind of transfer, there's going to be a change in temperature eventually on your hand. So effectively, the heat makes it from the coffee through the cup to your hand. However, there is no macroscopic motion. The motion is microscopic. So essentially, that's what conduction is. It's the same thing that happens. You are stirring your soup or you're making your cooking. Eventually, the spoon you're using to cook or the apparel you're using to cook eventually gets hot. Or you touch the sides of a pot, the handles of a pot, eventually they get hot. That's by means of conduction. The handles of the pot are not in direct contact with the stovetop, but somehow the heat from the stovetop eventually makes it to the handles and eventually to your hands. So the point is, that is how conduction works. It requires physical contact, and there is no macroscopic motion of particles, of molecules. Convection, on the other hand, requires a macroscopic motion of particles. For instance, when you open a window to get fresh air, actually what you're doing is you are allowing particles from outside, which had a typically cooler temperature than the particles inside the house. You are allowing the particles from outside to migrate into the room you're in, and as a result, because they are cooler, they eventually will drop the ambient temperature. And obviously the particles that were initially in the room, they migrate out, so they take energy. They move energy with them. They transfer energy with them. So the point is, all of the main contrast between conduction and convection is that with convection there's macroscopic motion of particles, while with conduction there is no macroscopic motion of particles, only micro. And obviously convection needs particles that are available to move, physically to move from one point to another. So as a result, convection is typically a useful, or rather employed whenever there's a fluid, whenever there's a gas that can move or a liquid that can move. That's the process typically that's used to move heat from one point to another. And then finally, there's radiation. Radiation is basically the transfer of energy via electromagnetic waves. And as we know, electromagnetic waves do not need a medium to propagate. They only need space or space-time. That's all they need. There's no need of microscopic particles, because electromagnetic waves are themselves, at least at the quantum level, they are themselves particles. They are photons. So these are the three methods that the universe transfers, or the three methods that the universe employs to transfer heat from one point to another point. Let's talk about each of these in a little more detail. And of course, the discussion here will be quite heuristic and not too in-depth. And for further discussion of these methods, I commend you the sections on chapter 14, section, I believe it's subchapter 4 to 14.4 to 14.7. That's where more details can be uncovered. But before we get into that, I wanted us to recap on what power is. Maybe you may have heard that the definition of power is the rate at which work is done. This is a sufficient definition in the context of mechanical systems, when we're dealing with mechanical energy, where work is being done, or rather, when work is done, there is a transfer of energy. However, the transfer of energy in mechanical systems is typically by a force. So it suffices for us to say, at least in that context, it suffices for us to say that power is the rate at which work is done. We could generalize this definition and apply it in the context of thermodynamics, where there's heat transfer. And we could say power is the rate of heat transfer. But remember, in this case, the energy that's being transferred here is due to a difference in temperatures, not due to a force being applied. But when two objects have different temperatures, there's going to be a transfer of energy, which we call heat. And the rate at which that heat is being transferred, we would call that power, and we would write it this way. Q here does not represent charge, it represents heat, as we have seen so far. And T represents time. And just as power was measured in watts in the context of mechanical systems, so also it will be measured in watts, even in the context of heat. Okay, now we're ready to go discuss further the different methods of heat transfer. let's start off with conduction. And as I gave you an example of conduction, that the context we see it in is here. I chose the example of a spoon in a hot bowl of soup. If you put the spoon initially, which is probably in some ambient temperature of a room, let's say 23 degrees, but your soup is quite warm, if you keep the spoon there, eventually after a while, the tip of your spoon, provided it's not insulated, eventually it becomes hot. How does it become hot? It's because there is an energy transfer from the soup to the spoon. And that means through which the energy is transferred in that context is conduction. There is no macroscopic motion of particles, but there is a microscopic collision of particles of the soup and with the surface particles of the spoon. Okay. Now the rate of conduction, the rate at which energy is transferred by the channel or by the method of conduction, depends on a couple of things. For that, I'm going to draw your attention to this drawing here. Over here we have an object which is hot and its temperature is T sub H, where H means hot. And on this side we have an object which is cool, whose temperature is Tc, so T sub C means a cooler temperature. And between these two objects, we have a medium through which heat can be transferred. Now, in order for heat to be transferred by means of conduction, there has to be physical contact between the hot object and the medium and the destination or the cooler object. Now, the rate at which heat is transferred from the hot object through the medium to the cooler object depends on a couple of things. The first one is what we call a temperature gradient. In other words, what is the difference between the two temperatures? What's the difference between the temperature of the hot object and the cool object? The larger the difference, the faster the heat transfer is going to be. Some textbooks, they use this, they write this as delta T. Please be careful. This doesn't mean a change in temperature. It simply means the difference between the two temperatures of the hot and the cold. And it will always be the temperature of the hot first minus the temperature of the cooler object, because we know the energy will always be transferred from the hotter object to the cooler object, never the other way around. Okay, so the temperature gradient is the first thing that affects the rate of heat transfer by means of conduction. Now, the second quantity on which heat transfer depends is the area of contact. In other words, what is the contact patch between the hot object and the medium, and versus the contact between the medium and the cooler object. You might consider this, that if you were to touch a stovetop with your finger versus your palm would have more energy transfer as compared to your finger, which means the larger the surface area of contact, the faster you can transfer heat. The more heat you could transfer per second, hence a faster rate. So the point is, the rate of heat transfer is proportional to the area of contact. And then the third thing on which heat transfer depends is the thickness of the medium. In our case here, the thickness is actually going to be, let's signify it as, this is how long this object is. This is what the thickness is going to be. The surface area is going to be this part, where the two contacts are, but then the thickness is how thick is the object to which heat is being transferred. you might imagine, I think this should be easy to see, that the longer this object is, suppose this medium through which we're transferring heat were longer, you see that it would take a lot more collisions between the microscopic, well, the particles. You would need a lot more particles to take part in this collision. Hence, it will take a lot more time for heat to move from the hotter object to the cooler object. So the point is, the rate of heat transfer is inversely related to the thickness of the medium through which we're transferring heat. And the final thing which heat transfer depends on is the nature of the medium. In other words, how good is the object, is the medium, how good is it at conducting heat? Some objects are better than others. You might imagine copper is much better than, let's say, leather or wood at transferring heat. Actually, coincidentally, this is the reason why sometimes when we touch metallic objects, they feel cooler than when we touch wood. The reason is, although the two objects may be in the same room, the metallic object is typically better at transferring heat fast. So the moment you touch it, you will immediately feel a heat transfer, hence it will feel colder. But wood is not very good at transferring heat. At least its rate of heat transfer is not as fast as for metallic objects. So that nature of that object also affects how fast we can transfer heat through that object. Actually, this nature of the object is called thermal conductivity and is represented by a lowercase k. Now, when we put all these dependencies together on the rate of heat transfer via conduction, we obtain what is known as Fourier's law of conduction. And the law mathematically looks like this. And as you can see, the rate of heat transfer is proportional to the surface area. In other words, the larger this patch, the more heat we can transfer. And the larger the temperature gradient, the more heat we can transfer. These are proportional. The thicker the object, the less heat we can transfer per second. And if the object to which we're transferring heat is a good one, then that will affect the heat transfer positively. So eventually this is how we summarize these dependencies. Note that the rate of heat transfer for the process via conduction will always be positive. Area is a positive quantity. Dimensions of an object are also a positive quantity. And this temperature gradient, because it will always be the larger temperature minus the smaller temperature, will also be a positive. And the thermal conductivity is always a positive quantity. So the heat transfer, or the rate of heat transfer through conduction, will always be positive. Okay, then let's move on to the second mode of heat transfer, and that is convection. Well, as I mentioned, that in convection we need a mass movement of particles from one point to another. If we are interested in finding out the rate of heat transfer by means of through conduction, we would need to find the total amount of particles that participated in the motion. And from there we could determine the mass. And by knowing the nature of the particles, in other words, what kind of particles were involved in moving or in convection, we could determine the specific heat capacity of that fluid. Suppose it was water flowing from one region to another, then we could use the specific heat capacity of water. Suppose it was air, again we would also do the same, because we could determine the content of air and figure out what particles were, how good are they at moving energy, and how much energy will they move. And we could also determine the resultant change in temperature as they move away. In other words, when the particles were in this region of space, suppose they were initially here, the temperature was a certain amount. When they move out, the temperature is at a certain amount. So we can determine the change in temperature due to their motion. And if we know how much time did it take the particles to move out of that region of interest, we can actually easily calculate the rate of heat transfer. We could calculate the heat involved in changing the temperature by the amount of particles that were involved. The mass could be using the mass which we obtained by determining how many particles were involved in the process and what kind of particles were they. Was it water? Was it helium, gas, or other substances? And then the change in temperature that they caused in their migration and the time it took for them to execute fully this migration, we can calculate the heat transfer due to convection. Note here that in this case, convection, in the case of convection, the rate of heat transfer can be negative because sometimes particle migration may take energy away from a particular region. For instance, you open your windows in order to cool your room down. They take energy away. When the particles move out of your room, they take energy away. But sometimes you switch on, let's say, a heater. A fan blows air into your room. That air is displacing cooler air and replacing it with warmer air. So in that case, the rate of heat transfer would be positive because the particles moving into your room are bringing in energy. So in the context of convection, we can have a negative rate of heat transfer. Okay. And then let's move to our final mode or method of heat transfer, and that is radiation. When it comes to radiation, the rate of heat transfer is governed by what is known as the Stefan-Boltzmann law of radiation. It is beyond our scope to motivate how we arrive at this, or rather how Stefan and Boltzmann arrive at this law. It takes a lot of statistical mechanics, but that's, as I've said, it's beyond our scope. So I will simply take this as an axiom, and I will talk about what all the different symbols mean. Okay, the first symbol we look at here is a sigma, lowercase sigma. This is what is called a Stefan-Boltzmann constant. This is a constant, and it's given by 5.67 times 10 to the minus 8 watts per square meter Kelvin to the power 4. This is going to be very important because this is going to limit us into what kind of temperature we can substitute here. The units of this constant, actually, they instruct us about this temperature. We will get to it shortly. Okay, the second symbol here, epsilon. Some books use an irregular E. I use epsilon just to avoid, because typically E is we use it for electrons, but I use epsilon for this case. This symbol here is a constant called the emissivity constant. This emissivity constant is simply a measure of how well an object can absorb or emit radiation, magnetic radiation. An object that is good at absorbing electromagnetic radiation is also good at emitting it. The more, if an object is a good absorber, it will also be a good emitter. So if it's very good at absorbing, then its emissivity constant will be large, closer to 1. But if it's a poor absorber and emitter, its emissivity constant will be closer to 0. Actually, in physics, we also have this thing called a black body. A black body is a perfect emitter and absorber. In other words, it will emit all kinds of radiation. It emits all the available radiation, and it can also absorb all kinds of radiation. Some objects are very good at absorbing infrared radiation, but very poor at absorbing UV radiation. So they would have a certain emissivity constant based on their properties of how well they can absorb or emit radiation. But an object that is good at absorbing all kinds of radiation is typically called a black body. Actually, when an object is poor at absorbing radiation, it means it's a good reflector. That means whenever radiation comes to the object, it reflects it. It doesn't absorb it, it reflects it. Therefore, its emissivity constant would be 0. Actually, that's what mirrors are. Mirrors, they typically, they reflect a lot more of the incident radiation than they absorb. Of course, they may absorb a certain amount, but it's a very small percentage compared to how much they reflect. Okay, and I should say the emissivity constant is something that is a property of the object of interest. And we will always be supplied this. We could always read it up from some tables where they are determined for us. So it's not something that we know universally. Okay, and then the third symbol is A. Here A is the surface area of the object of interest. If we're interested in an object that is of this shape, that is kind of like a cube, then we would need to find the surface area of the cube, the total surface area, because the cube will be emitting or absorbing from all angles and all faces. If it's a sphere, if our object is a sphere, then we know we would need to use the area of a sphere to calculate how much radiation, how well it absorbs radiation, or rather how fast it absorbs radiation. Okay, and then finally we have T here. T here is a temperature. However, specifically it has to be the temperature in kelvins. This equation here, by virtue of this Boltzmann constant, demands that the temperature should always be in kelvins in order for us to employ Stefan Boltzmann's law of radiation. It is very important that the temperature here is what is called absolute temperature. We don't have an option of using degree Celsius or degree Fahrenheit, but we have to use kelvins. Okay. Now, over here I haven't specified anything about the object. Let me give you a little bit more of a handle of how this works. First things first, it is important for us to know that all objects, no matter the object, all of them, they absorb and emit radiation. These processes are true for all objects. Some objects are very good at absorbing some form of radiation and not some other form. But the point is, all objects absorb and emit radiation. For instance, you might look at a red shirt in a room that's lit. So the lamp in your room is white light, which contains all the colors. Your shirt absorbs that light, but it will emit a red light. So it's good at absorbing, it absorbs light and it also emits, but it's very good at emitting red light. That's the key. That's why you see a red shirt. It's because the pigments on the fibers on your shirt have a pigment or a dye which is very good at emitting red light. That's why the shirt appears red. That's just a simple example to argue and hopefully convince you that all objects actually both absorb and emit radiation. Okay, now let's consider an object that is placed in a room or in some environment. This is, we're trying to get to the point where we can hopefully assist in giving you a handle of how to use Stefan Boltzmann's law of radiation. Consider an object that is placed in a room. Here's our object represented by OBJ, and it's in a room represented by, well, room. And sometimes we might not call this a room, we might call it an environment. So it's placed in some kind of environment. Now, if we are interested in how much radiation the object emits, we would need to use Stefan Boltzmann's law of radiation in this way. This is what we would use. The amount of radiation an object emits depends on its temperature. The hotter an object is, the more radiation it will emit. The cooler an object is, the less radiation it will emit. So the point is, when we are interested in how fast is an object emitting radiation, we would need to use Stefan Boltzmann's law of radiation, but the temperature here would be the temperature of the object. And obviously the area would be the area of the object, and the emissivity constant will also be the emissivity constant of the object. And obviously sigma is a constant, which we already know of. This will enable us to figure out how fast is an object transferring heat by means of radiation. Okay, but what if we are interested in how much energy or how fast is the object absorbing energy? Well, we would use the Stefan Boltzmann's law of radiation again, but the difference this time is that the temperature we will use is not of the object, but of the room. Of the room. So the hotter the room, the more the object will, the more radiation, or rather the faster the object will receive radiation from the room. And the area here obviously would be the area still of the object, but not of the room, but of the object, because that's the surface onto which the object can receive this radiation coming from the room. And the emissivity constant is a property of the object, so that will tell us how well it absorbs radiation, the object absorbs radiation. And as again, sigma is a constant. It is very important that whenever you are interested in how fast is the object absorbing radiation, we use the temperature of the environment. However, when we're interested in how fast the object is emitting radiation, we use the temperature of the object. That difference is very important. And to conclude this already lengthy video, typically we are interested in the net rate of heat transfer by radiation. Sometimes we're not interested in how fast is the object emitting or how fast is it absorbing. Sometimes we want to find out what's the net. Is the object gaining energy or losing energy? Well, in order to determine that, by definition, and I should say that this is definition, the net rate of heat transfer is by definition given by the rate of absorption minus the rate of emission. That's the net. The net is equal to how fast are we absorbing minus how fast are we emitting. If we're absorbing faster than we're emitting, we can conclude that the room is hotter than the object. In other words, energy is flowing from the room to the object. However, if we're emitting a lot more than we're absorbing, that means heat or energy is flowing from the object to the room. Hence, the room must be cooler than the object. And I repeat, this is a definition for the sake of convention. It will always be the absorption minus the emission. And if we're to plug in these values or these formulae into this equation and take out the common factor, what we would obtain is that sigma epsilon alpha, open bracket, the temperature of the room to the power 4 minus the temperature of the object to the power 4. And these temperatures must be in kelvins. Maybe one more thing as an aid. This is not equal to, I should say, this is not equal to, this is a typical mathematical error of notice people make, but I would like to point it out while we're at it. It is not true that the difference of the fourth powers is equal to the fourth power of the differences. Notice here the 4 is outside the parentheses, but notice over here the 4 is actually inside, is on the temperatures themselves. So please avoid this mistake. But in order to not add too much detail, I will conclude the video here, and we will have follow-up videos for examples. And see you on the next one.